Okay, so let us start our class today. We'll be doing chapter 4 force in this 1 hours. Okay, hopefully we can finish it within an hours. All right, so force. Okay, forces. 4.1 basic of forces and the free body diagram. So we're going to see how many types of forces are there, and then how are we going to sketch free body diagram based on the informations given. So force is defined as a physical quantity which causes an object to move, to stop, to changes its direction, or changes its physical form. So anything that can causes these four actions, okay, we call it a force. So a force is a push or pull on the object. Either you push it or you pull it, and then it is a vector, which means if question asks you to calculate force, once again, you need to state its direction because it is a vector quantity. So a force requires an agent, means that you need some things in between there for it to do a pushings or pulling. Okay, so a force has a specific or identifiable cause. So you can identify it based on the situations given. What type of force, okay, are we looking at? So a force is either a contact force. Contact force means two objects are in contact, they are touching each other, or a long range force. So long range force, we refer it to a gravitational force. Okay, so gravitational force is chapter 7. We'll look at it soon. All right, or another long range force would be a electric force. Okay, you have a charge, two charge that is far apart, and then they have a force, the experience attracting or a repulsive force between them. So that is what we call long range force, no touching. So a contact force is our main focus today. So SI units of force is a kgms negative 2 because of we have equations MA, or Newton, okay, which is a special SI unit. So both of them, they are SI unit, just that one is a special SI unit, another one is in terms of base unit. Right, so today we are going to look at 5 types of force. Okay, 5 different types of basic force. First one is weight. Now, don't get confused between weight and mass. Weight and mass, they are a different thing. All right, so weight is defined as a force exerted on a body under gravitational field or near the surface of the earth. So it depends greatly on G. Okay, whereas if you're looking at mass, it isn't being affected by anything. Okay, it doesn't being affected by the gravitational force. Whereas weight, it depends greatly on the gravitational pull. So which means if you're on different planet, you will have different weight, but the mass would be the same. Okay, mass is fixed, and then weight, it depends on where are you. It depends on the gravitational force. So the agent for weight is the entire earth that is pulling on the object, which is your gravitational pull. Directions of the weight, it is always pointing downwards. So this is very important. It doesn't matter where is your object, how does it look like, okay, how you put it, how you place it on the surface, it is always downwards. Okay, so the force always moving down, right, pointing downwards. So let's see. If you look at the object, the diagrams on the right hand side, first you have an object, you place it on the surface. So this one, obviously, W is straight away going down. Okay, this is our W. Now, how about the objects on the slope surface? If you look at the words that I highlight here, it tells you it doesn't matter where is the object, how do you place it, the directions of the weight vector, it's always downward. So means that even if you put it on a slope surface, this is how it looks like. This is the weight. Okay, this is the weight. So it is always pointing downwards. Okay, it doesn't matter how do you put it. So for example, now if you put a surface, okay, you press the surface against wall. Okay, you press it against wall. Directions of weight also pointing downwards, also going down. Okay, so it has nothing to do with the surface. It has nothing to do with how you place it. W always pointing downwards. So the equations for W, okay, since we say it depends on the gravitational pull, so W is equals to mg. Okay, so gravitational pull is a direction, is a vector. Therefore, W is also a vector. All right. So m, remember, m is different than W. All right, M refers to mass. Mass is constant regardless of where you are, and then weight, it depends on the G. Okay, which means it depends on the altitude of the object. It depends on the planet that the object is staying on. And the next one is tension. Okay, the second types of a force that we're going to look at today is tension. So when a string or rope or wire, so these are the keywords. So whenever you have all these objects, okay, whenever you have all these three items, it means there must be a tension in the diagram, in the situations given. So just now, it doesn't matter which object you're looking at, as long as you have an object, every object comes with weight. Now you look for these three terms, okay, in the questions. Or sometimes maybe you have a strings, you got strings here, you got a rope, you got a wire. Usually that's what we have in the questions. So if you have these three things in the question that is pulling on the object, that's being attached to the object, then we know there is a tension. Okay, so we call it a tension force. So the agent for tension force is a string, rope, wires, and a string-like object. Okay, string-like objects. So directions of the tension is always away from the object. Now, actually, to be more precise, tensions is moving towards both direction. Okay, just that when we draw the diagram, when we sketch the free body diagram, then we sketch it away from the object. So for example, if you look at the diagram on the right hand side, the directions, now this string is being attached to two objects. Now why I say two objects? Object 1 is actually the wall. Object 2 is our square box. So we have two objects that is being connected by the string. Therefore, both of them, they experience tension when you pull the string. So tensions, the directions of the tensions according to the questions, according to the notes given, it is always away from the object. So now both objects, they experience a tension force. So the tension would be like this. Okay, both objects, they are being pulled by the string. Therefore, the force is away from the object. So you hang the box here. Okay, you hang a box here. This box actually is pulling the wall. Okay, therefore you have a force that is coming out from the wall. But at the same time, okay, this is because of Newton's third law. At the same time, this wall is pulling the object as well, so that it won't drop on the floor. Therefore, there's another tension pointing towards opposite direction, which is the tensions coming out from the object. Okay, so I repeat. First, we have a object. Okay, when you hang an object, this object is actually pulling the wall. Therefore, you have a force coming out from the wall. Okay, you have a tension coming out from the wall, which is a tension number 1 here. So this tension number 1 belongs to the wall, because wall now I call it object number 1. So at the same time, this wall is pulling the boxes. Okay, it's pulling the box so that the box won't drop to the floor. So since it is pulling the box so that the box won't drop, therefore the tension acting on this box is going upwards, right? And because they are being joined, being connected by the same string, therefore in this case, I can say T1 equals to T2. Okay, and that's why in my diagram, I just call it T. All right, so if you are looking at same string, it means they have same tension, right? It means they have same tension. So the tension is the same at all points in the rope. Okay, that's why you have T1 equals to T2. So symbol is T. Now, how about diagram, the second diagram? Now you have two boxes, okay, and actually they are pulling each other so that they won't drop. So for object A, the tension is like this. Okay, so you have two tension. One tension is pointing downwards, another tension is pointing up. And then for object B, same things happen. Okay, same things happen. Just that in our calculation, we are just going to look at one tension, which is this one. Okay, if you are looking at object A. So if you are looking at object B, then this is the tensions that we're going to look at. Now, one thing about this diagram is now because, well, if you look at this diagram, these two objects, they are being connected by the same string, okay, over a pulley. So this is pulley. So these two objects, they are being connected by same string. Therefore, I can conclude that TA is actually equals to TB. Okay, TA is actually equals to TB. So which is T. That's why I label T in my diagram. Right. So of course, if the pulley is not frictionless, then you cannot say TA equals to TB, right? So in this case, the example given here, I assume this is frictionless, no friction, okay, frictionless pulley. Therefore, I can say A is equals to B, all right? So case number 1 is T1 equals to T2. So when you have a second case, now because you're looking at same string, so if they are being connected by different string, so I'm just going to give you one more example. So for example, now you have a floor, then you connect this object 1, okay, and then this object 2, and then this object 3. So you pull object 1. When you pull object 1, okay, I'm going to call this external force because this is exerted by you. You pull it. So when you pull it, it's moving. So this is a string number 1. Therefore, string number 1, it has T1. Oh, it's T1, not T2. All right. And then for the second string that join object 2 and object 3 together, now because it's no longer being connected to object 1, and now it's a different string. Therefore, this is T2. Okay, and T1 is not equals to T2. All right. So this is another example. And why T1 is not equals to T2? They might be equals, might be equals, but most of the time they are not equal. So the reasons why I know they are not equal, that is because now I have two different string, right? So this is my string number 1, and then this is my string number 2. So now I'm looking at different string. So different string, they come with different tension. So in a diagram above, because you're looking at the same strings, therefore they have the same tension. Okay, so this is the second type of the force. Now the next one is friction. Friction is slightly more complicated. Why? Because we have two types of surface. So friction is defined as a force that opposes the relative motions of two surfaces in contact. Now, when it comes to frictions, the things that we need to see is whether the surface given is a rough surface or a smooth surface. If it is smooth surface, then we ignore friction. So that is a key things. That is a key part that we're going to look at. We're going to check in our question. What types of surface are given? Is it a rough surface or a smooth surface? Okay, so the agent for friction is a rough surface. Or sometimes questions will just give you a symbol called mu. Okay, the values of mu. Now, what does it mean by mu? So you look at the equations given, it is a coefficient of friction. So whenever you are given the values of coefficients of frictions, it carries a hidden meaning where now you have a rough surface. So in our syllabus, the surface is always smooth, unless questions tells you it is a rough surface, unless questions give you mu, the values of coefficients of friction. So friction is directly proportional to the reactions force. Therefore, we have F equals to mu N. Okay, F equals to mu N. So this is very important. Usually questions won't give you the values of friction straight away. It will give you coefficients of frictions. You yourself need to identify N from the question first in order to calculate friction. Okay, so this one you will have quite a lot of questions in your tutorial class. So I will leave it to your tutorial lecturers to explain it. So coefficients of friction is defined as a ratio. Now, if you look at this equation, coefficients of friction, frictional force divided by normal force. Now, force divided by force, which means your coefficients of friction is a dimensionless quantity. All right, dimensionless quantity. What does it mean by dimensionless? No unit. So it is just a value without unit. Okay, it is just a value without unit. So the mu depends on the nature of surface. So if you are looking at the same surface, then it means same surface and same object means that you're going to have the same mu. If you're looking at different surface, then definitely it will have different mu. So there are three types of friction. Okay, but in our syllabus, we are just going to look at static friction and kinetic friction. All right, rolling friction is no longer in our syllabus. So static friction. Now, what does it mean by static friction? Object is not moving, right? So how can it experience friction? Now, the reason why object is not moving, that is because there's a friction prevent it from moving, stop it from moving. So in that case, we call it static friction. So frictional force acting on an object before it move, okay, before it move. Or, okay, the directions of a static friction, it points in the directions that is necessary to prevent the motion. So now what does it mean? To prevent the motion. So how are we going to guess the direction? Let's see. If you look at the diagram again on the right hand side, static friction. Now this static friction object is not moving. If you look at this object, this box, by nature, if we have a smooth surface, then our object it should go downwards. All right, this is by nature. By nature, the directions of motion should be going down. Therefore, if the object is not moving, what does it mean? Okay, if object is not moving, so I'm going to erase it first. It means there is a frictional force acting in the opposite direction that stop it from moving, that prevent it from dropping, from sliding down. Therefore, this one we call it F, and now because we are looking at static friction, we put a subscript S here. So Fs, okay, Fs. So it prevents object from moving. So your object will stay at this position without moving with the frictional force going up. All right. Now for this not moving object, actually there are two forces acting on it. One force is a frictional force. Okay. So another one is the weight. So weight is still going down. All right. Weight is still going down. Of course, our main focus in this diagram is a frictional force. So make sure you know how to determine the directions of the static friction. So static frictions, you look at the nature, the directions of the object by nature, provided if there's no frictional force. What is the direction that is going to move? So now in this case, if there's no static friction, if you have a smooth surface, by right, it should slide down. Therefore, we know that the direction of frictional force is definitely in the opposite direction, which is going up. Okay, going up. So keywords used in exam. So just now it said before it moved. Actually, there are a few more keywords that we use to identify whether it belongs to kinetic friction or static friction. Now, it is very important to know which frictions you are looking at, because sometimes questions will give you both the coefficients of static friction and the coefficients of kinetic friction. You yourself have to know which one to use in your solution. So if you have a static friction, the keyword is the object is about to move. About to move. Just before it begins to move, before it starts to move, or just right when it starts to move. Okay, just start to move. So it's not moving for long, it just starts. Okay, when an object just starts to move, or when it's about to move, just before it begins to move, or before it moves. Okay, so all these words, these are terms that we use to identify, okay, whether it is static frictions or kinetic frictions. If you have all this term, okay, if you have all this term, then it means this object is experiencing static friction. Okay, it has a static friction. And then kinetic friction, okay, kinetic friction, in other words, we call it dynamic friction. Kinetic is moving, so dynamic also moving. So kinetic frictions also known as dynamic frictions. And the symbol we use is Fk. K stands for kinetic. So frictional force acts on an object when it is moving. Okay, now your object starts to move. So now it has a kinetic friction. So kinetic friction is very easy to identify the direction. It is always in the opposite directions of the velocity. So velocity, usually we call it the directions of motion. Okay, velocity shows us the directions of motion. So frictional force is always in the opposite direction. So for instance, if you look at the diagram on the right-hand side, now you have A going to the right, therefore your F is going to the left. So second diagram, your V going down, therefore your Fk is going up. Okay, your Fk is going up. Now, not just V, sometimes questions might give you symbol A. So A is also represents the direction. For example, now you're given a surface, it tells you now your object is moving with a constant accelerations to the right. Therefore, our frictional force is also going to the left. So A and V, it tells us the directions of motion. Okay, it tells us the directions of motion. So not just velocity, but also acceleration. And then the last one, okay, the last sentence is important, especially in the objective questions in your UPS. The values of kinetic frictions between the surface is always less than the values of static friction. Okay, is always less than the values of static friction. So Fk is less than Fs. And because we have F equals to mu n, okay, so based on this equation, F is directly proportional to mu. Therefore, we can conclude that mu k is always less than mu s. Okay, mu k is always less than mu s. So these two things, it can come out in our objective questions because it doesn't require you to do much calculation. It just needs you to understand a bit of concept. So these two value, it also tell us one information. In order to initiate a motion, you need more force. But once the object start to move, less force is needed, okay, to maintain the motion. So it is always harder to move an object. But once it starts to move, when it begins to move, then you need less force to keep it moving. Okay, so this is the information that you can get based on this relationship. Fk is less than Fs, or mu k is less than mu s. Right, so this is our frictional force. Normal force. So normal force is defined as a reaction force, okay, that is being exerted by surface. So which means you need a surface in order to have a normal force, the reaction force. So the symbol can be a N or R, okay, it depends, it's up to you. So the directions of normal force is always perpendicular to the surface. So if there's no surface, for example, if you have a hanging object, then there's no normal force. Okay, normal force, there must be a surface and our object must be in contact with another surface. Not necessarily the floor. Okay, if you are placing an object on top of the other object, they will also experiencing normal force or reaction force. So you look at the diagram on the right hand side again. Now this is our surface. Okay, the surface. So the surface is on the ground. Is the ground. So the directions of normal force, it's always perpendicular to the surface. So this is a normal force. So it is perpendicular, right? So for the second diagram, now we have a vertical wall. Okay, we have a vertical wall. Therefore, normal force is going to the left-hand side, perpendicular to the surface. All right, so it doesn't mean that normal force always pointing upwards. This is a misconception among students. You guys always thought that normal force is pointing upwards. No, it's actually perpendicular to the surface. So for example, now if you have a sloped surface, right, and then you put an object here. So surface is this one, okay? So you have a surface here. So this is your surface. Okay, this is the surface. So a normal force is perpendicular to the surface. So this is a normal force. So it is not a horizontal, it is not vertical, but it is located in between X and Y axis. So you might need to resolve it in your calculations. Right? So
Dalam contoh,
yeah.
Macam kapal terbang.
Okay.
Atas, daya ke atas tu ialah normal force kan?
Bukan, itu adalah lift force.
Lift force, okay.
Daya apung. Dia tak ada daya normal sebab dia tak in contact. Kalau kapal terbang ada normal force, itu bahaya dah. Okay. So last one. Okay, last one is the external force. Okay, now external force here or the other type of forces. Okay, we put it under external force. So most probably it is being refers to pushing or pulling force. Okay, either you pull or push an object. Okay, it is caused by usually we say it's caused by human. Okay, because you're the ones that doing the pushing or pulling. So external force is a push or pull on the object. So if you look at the diagram, even if you pull the string, then here we call it external force. That's why in the diagram above, okay, in this diagram in the tension, okay, I call this one F external. because this is being caused by you. You are the one that pulling the object. I don't call it tension. All right. So external force is a push or pull on the object. So the symbol is either F only or use UFP. But personally, I like to use FEXT. Now this subscript actually is up to you. Okay, what is the names that you want to give it? Sometimes students call it FA, FB, F Ali, F Ahmad. Okay, all can, as long as you label in the diagram. Okay, because you just need something to tell you this one is an external force. Okay, so direction is given in the questions, or now if you pull the object, definitely the force is away from the object. Okay, let's say this is the object, so you pull it, this is your F. All right, now if you push the object, remember, if you push it from the left hand side, then the force will come out from towards the right hand side. Okay, because they are exerted a force into the object, and we know that vector cannot entering an object, cannot goes into the object. It must comes out from the object. So if you push something, then the force will come out from the other side. Okay, the force will comes out from the other side. So this is how we identify the directions of the force. Okay, now before we move to a Newton first, second, and third law, I wanted to copy something, this one. So how do we identify forces? So I give you a summary here. Always ask yourself 5 questions. Okay, is there mass of object? So we want to identify whether we got a weight or not. So if got mass, then it has weight. So basically everything on Earth, it comes with weight. So weight, you can say it exists in every single question, basically. And the second question you ask yourself, is the object in contact with any surface? If it has a surface, then we have normal force. If no surface, then no normal force. Is the coefficient of frictions given, or is it mentioned that the surface is rough surface? If got, then we have frictional force. If no, then no frictional force. Is there string, rope, chain, or wire connected to the object? If yes, then there is a tension. If no, then no tension. Then is there any applied force, for example, pushing or pulling by the human acting on the object? If yes, then external force. If no, no external force. So whenever you try to answer a question that is related to force, try to ask yourself these 5 questions. Okay, does it has any of this one in the mentions in the question? So from here you can identify what type of force that you are dealing with. So I want you to write it down. Okay, I want you to write it in your notes, because this helps you to identify what type of forces that you're looking at. Okay, so I give you 2 minutes to, and 2 minutes, 3 lah. I give you 3 minutes to write it down. Okay, 3 minutes to write it down. Write it down in your notes before we proceed to the next subtopic. Okay. So before we proceed to the next part, okay, there's one more thing that I want you to take note, which is a free body diagram. So a free body diagram is very important in chapter 4. So what does it mean by free body diagram? Free body diagram is a diagram that shows all forces acting on just one object. So when you want to sketch free body diagram, if the questions ask you to sketch free body diagram, okay, because sometimes questions will state that, state free body diagram for object A. Okay, then you have to know you cannot draw a box in your diagram. Okay, in free body diagram, the object is represented by a dot. Okay, so the force arrow is drawn from the center of the point and then it's go outwards in the directions of which force is acting at. So for example, now let's look at the diagram here. Okay, now pay attention. Yeah, this is not in your notes. So if you have a rough surface and then you have a pushing force from the left, so what is the force acting on my object right now? So this is the center of the object. So object, try to ask yourself that 5 question. Now this is an object. Every object comes with weight. That is what we know. So weight is going down. And then the second thing, is it in contact with the surface? Yes, it is. This is a surface. Okay, it is in contact with the surface. Therefore, we know it comes with a normal force. Now you have an external force that is pushing it. So when you push an object, the force will come out from the other side. That is what I told you just now. And because you have a rough surface, okay, so therefore rough surface, Fk is going towards the other direction. So when you want to sketch a free body diagram, you look at the one on the right hand side. That is how you do it. You use the dot to represent the box now. Okay, so this one represents object. So the force, all 4 forces, they are coming out from this dot. So this is a complete free body diagram. So usually in questions, one free body diagram, it worth up to 2 marks. All right, so 1 mistake minus 1 marks, 2 mistakes straight away 0 mark. Okay, or sometimes they look at the label. So make sure you use a correct label. N or R to represent normal or reaction force. Capital letter F to represent external force. W to represent weight. Small letter f to represent friction. And T for tension. So all these symbols must be correct. All right, you can play with the subscript for external force, but not the rest. The rest, they have their fixed symbol already. You cannot use the wrong symbol. All right. Sometimes if you use the wrong symbol, it's considered as wrong in the exam. So make sure you use the right symbol. Capital letter F, external force. Capital letter N or capital letter R refers to a normal or reaction force. Small letter f is for frictional force. Capital letter W is for the weight. Capital letter T is for tension. So make sure you use the correct symbol. So this is free body diagram. So you have to know how to sketch free body diagram. So sometimes even if the questions didn't ask you to sketch free body diagram, I would like my students to draw it because it helps you to see what is going on, what is happening. Okay, how many forces do you need to solve? All right, and then what is the directions of the force? Do you need to resolve them, or you don't have to do a resolving vector? You can straight away calculate the total force. So all those things, okay, all those things you can see from the free body diagram, whether the questions given is a 1D questions or a 2D questions, whether you need to resolve the force or not. It's all in your free body diagram, right? So resultant force. So resultant force is also known as the net force. It is defined as the vector sums of all force acting on the object. So if both forces are acting along a straight line, which is the same component, then you can just add or subtract it. That's why I say it's very important to see the free body diagram. If you're just looking at one component, for example, just the x component, and all forces they are lying on the x component, then done. You can just add or subtract it. If not, okay, if both forces they are not acting in a straight line, then you have to use resolving method. How to resolve it? You refer to your Sem 1 notes. All right, you refer to the Sem 1 notes and Sem 1 chapter 1. All right, so net force, okay, resultant force. So questions often ask you to calculate resultant force. Then you have to see how are you going to calculate it. Okay, let's go back to your note. So state Newton's law of motion. That is a second subtopic in chapter 4. So Newton's first law. We have Newton's first law. It states that an object at rest will remain at rest. or when it is moving with constant velocity. That is the key words. So Newton's first law, object move with constant velocity. Okay, in a straight line, will keep moving in a constant velocity along the same straight line unless you have an external force acting on it. So the first law gives the idea of inertia. Inertia means that the tendency of an object to resist any changes in its state. So for example, if you put a coin on top of a cardboard and then you put a glass here, when you pull the cardboard away from the glass, okay, you pull it quickly. If it is quick enough, then the coin, it won't have a time to react. So it will resist the change and therefore it will drop into the glass. So mass is defined as the measures of a body inertia. The values of mass is independent of location. So that is why I told you just now. Regardless of where you are, okay, mass is always the same. So the mass of a body increases if the mass of the body increases, then inertia will increase. So it will be harder to change its motion. So mass is a scalar quantity and the SI unit is kilogram. All right, now, equilibrium of particles. Okay, so equilibrium of a particles is defined as the vector sum of all forces acting on the object that must be equals to 0. So F net, okay, F net equals to summations F, and it is equals to 0. Now, how do I know it is equals to 0? If you recall, what is the equation for force? F equals to ma. But according to Newton's first law, my object is moving with, okay, constant velocity, okay, constant v. So if it is moving with constant v, then what does it mean? Constant v means A is equals to 0. Therefore, total force acting on the object is equals to 0. The vector sum of all forces acting on the particle must be equals to 0. Right? So the equivalence of three independent scalar equations along the directions of coordinates exist. So if you have an object where the force, they are not acting on the same straight line and you want to solve the question, yes? Okay, and you want to solve the questions, what can you do? You solve them by component, right? So provided if you have a three component, x, y, and z, then you can say summation fx is equal to 0, which is total force acting along the x component. And then summations Fy, total force acting along the y component. Summations Fz is total force acting on the z component. All three components, they are equals to 0. Okay, the total force, not individual force. Individual force might not be equals to 0. Okay, so for example, now you have a case like this. This is the example. So you push an object. Okay, this is you pushing an object. And then this is a rough surface. So if you push an object, now I'm going to push a free body diagram. The force is going to the left-hand side. Okay, so this is a non-zero value. This F is not equals to 0. And at the same time, there is a frictional force acting in the opposite direction. Again, it is not equals to 0. All right, and then this is an object come with weight. Again, weight is not equals to 0. And then this object is in contact with a surface. So normal is not equals to 0. All right. So what can we say now? If the question tells you now this object is moving with constant velocity. Okay, constant velocity. So usually if it says constant velocity, diagram will give you symbol V. Okay, we'll give you symbol V. V means object is moving with constant velocity. A means object is moving with constant acceleration. So if it says object is moving with constant velocity, what can I do about this given example? I'm going to solve them by component. Now I have X component and also Y components here. X component, I have two forces. According to Newton's first law, equilibrium of particle, summations Fx is equals to 0. Now that I have two forces, I have F, external force going to the right-hand side, so positive F, plus, now frictional force going to the left, so plus negative frictional force. Okay, so total is equals to 0. So that is what it meant. All right, total force, summation Fx is equals to 0. So when you add them up, total is equals to 0. If you rearrange the equations, you will see that the reason why my object is moving with constant velocity, it is because external force is equals to frictional force. So same goes to a component, a y component. So now I want to solve them according to component. So summations fy is now equals to 0. Okay, because now I say the object is in equilibrium. So object is in equilibrium, summations fy is equals to 0. So now I have two forces along the y component. Okay, this is along the y component. Therefore, what can I say? I have a normal force going up, so positive n plus w is going down, so plus a negative w equals to 0. All right, so the terms on the right hand side, you don't have to change it, you don't have to do anything. So in that case, if you rearrange the equation, it tells you that if the object is in equilibrium, my n is equals to w. So you solve them by component, okay? You solve them by component. So x component, and then you have a y component. This is x, sorry. So x component and x component, y component and y component. You solve them by component. So when it comes to force, usually it's a two-dimensional questions where you have to solve them according to its component. All right. So according to Newton's first law, okay, there are two types of equilibrium. One is a static equilibrium, in which v is equal to 0 or object is at rest, not moving. Okay, not moving. And the second one is dynamic equilibrium, where your object is moving with constant v. So either v equals to 0 or v constant, it gives you f equals to 0. Okay, because you're using ma, so constant v give you a0, and then v equals to 0, a also equals to 0. So it doesn't matter whether the object is in static equilibrium or in a dynamic equilibrium. As long as it is in equilibrium, then total force acting on it, the vector sum of all forces acting on it, it is equal to 0. All right. So that is your Newton's first law. Newton's second law. Okay, Newton's second law, it tells us that the rate of change of momentum of a moving body is proportional to the net force, and is in the same directions as the net force acting on it. So rate of change of momentum, that is dp over dt, rate of change. Whenever you have the terms rate, means something divided by time. So rate of change of momentum is a momentum divided by time. It's proportional to net force. Therefore, the equation is summations f is directly proportional to dp over dt. Okay, dp over dt. So net force is your summations f, and then the rate change of momentum. So rate of change, whenever you have the terms rate of change, means it's something divided by time, right? So from here, you then derive the equations. So Newton's second law can also be written as summations f equals to dp over dt. P is equals to mv. That is from what we learned in chapter 3. Sub it into the equations. Then you apply this one. I can't remember what it called in mathematics already. Okay, so summations f is equals to v dm over dt plus m dv over dt. So this one is a part of mathematics. So from here, okay, since mass is constant, therefore the change when you differentiate it, it is equals to 0. All right, so therefore f is equals to m dv over dt, which means it can be written as summations f equals to ma. So this is the most important equation in Newton's second law. So in Newton's second law, okay, it means, okay, it says that direction, the force, the object is moving with the constant acceleration. That is keywords, because now you have an equation that come with a. Therefore, in this case, we have something that is moving with constant acceleration. So this is the keywords that tell us whether we need to apply Newton's first law or Newton's second law. If your questions tells you object is moving with constant, v, or at rest, then we apply first law. Okay. If questions tells you object is moving with constant a, then we apply Newton's second law. Okay, so first law and second law, they have their own keywords. You try to search for the keywords. The questions will tell you what types of motions that you are dealing with, whether it is constant accelerations or constant velocity. So again, since a force is a vector quantity, you need to resolve it according to its own component. So for instance, summations fx equals to max, summations fy equals to may. So x component, you look at ax, y component, you look at ay. So the directions of force is same as the directions of the acceleration. So for example, now I give you the same example. Okay, I have a box and then you're pushing it. So you're pushing it and then this is a rough surface. But now my object is moving with constant A. So what should I do? Again, I'm going to draw a free body diagram for it. External force going to the right, frictional force going to the left, Fk, and then normal force going up and weight going down. Now, when it comes to these questions, how am I going to solve it? Let's look at x component first. So x component, I'm going to use summations fx equals to, now, should I use first law or second law? You look at the diagram. Diagram tells you your constant accelerations is happening along x component. Therefore, for x component, we use max. So when you want to form equations, you keep the max on the right-hand side. You don't do anything. You don't change anything. Okay, and when it comes to chapter 4, usually we take direction A as positive direction. So max, you leave it. Now, what are we going to do? We are going to expand the equations on the left-hand side. You look at the diagram. Along x component, I have external force and frictional force. Okay, I take directions of A as a positive direction. Therefore, now my F is positive plus negative Fk. Okay, plus negative Fk. This is for x component. Okay, for x component. But how about y component? If you look at the questions, this is my y component. Is there any motions along y component? Obviously no, because now my object is moving along x component, is moving horizontally. It doesn't move up and down. Okay, so in that case, for y component, what are we going to do? So we are going to use summations fy, but now there's no motions along y component. My object is moving with constant accelerations along x component, not along y component. And my object, it doesn't jump. It doesn't jump up and down. Therefore, for y component, we apply Newton's first law because there's no motions along y component. Now you see, we can have two different laws acting on the same object. One is you have to see what is the directions of motion, where is it? Is heading up and down, or is going to the left or right? And then you have to determine which law to use. Usually one second law, one first law. Okay, or maybe you can have two first law, but I don't think you can have two second law. Okay, because an object cannot move in two directions at the same time. It's either moving along x component or it's moving along y component. Okay, it can't move towards x and y at the same time. Unless you break the object apart, then yes, it can happen. So for y component, I'm still going to do the same. So n is positive plus a negative w. So equals to 0. So x and y component, different law. X component, I use second law. Why? Because accelerations, constant acceleration is happening along x component. Whereas for y component, object is not going up or down. Therefore, summation f equals to 0. Okay, so this is very important. Okay, now let's look at the last page of your notes. Okay, Newton's third law. So Newton's third law, what does it mean? It means every action force. Now, I want you to highlight keywords because sometimes question will ask you to explain what is going on. And you have to explain by using words. So in your explanation, the terms that you must have is action force. Every action force, it must have a reaction force that is equal in magnitude, but opposite in direction. These four keywords, you must mention it in your explanation. Okay, you must mention it in your explanation. Which one is your action force? Which one is the reaction force? But then the force acting on them, they are equal in magnitude and they are opposite in direction. So in yes?
Ni third kan madam kan?
Apa?
Bukan second law kan?
Ini third law sudah, Newton's third law.
Dia
Oh,
tulis.
okay, typo sini. Thank you. So Newton's third law states that every action force has a reaction force that is equals in magnitude but opposite in direction. So these four keywords. Okay, so cara bagi markah, the ways we give mark in your explanation types of questions, we will search for these four keywords. Right. So if two objects interact, then force F1 exerted by object 1 on 2. Now 1, 1, 2 means exerted by object 1 on object 2 is equals in magnitude but opposite direction to the force F21. F21 means exerted by object 2 on object 1. Now actually this subscript, double subscript notation is arguable. Okay, so it doesn't matter whether you write F12 or F21 as long as you show it in your diagram. Okay, as long as you show it in a diagram. Because some books they use F12, some books they use F21 to represent a force acting on an object 2 by object 1. Okay, so ada yang guna on by, ada yang guna by on. So double subscript notations actually is quite arguable, and usually I just write one subscript. So for example, if I have a two object, let's say I have what? I have two object. I'll explain with the diagram later. So if you have two forces, what can you say? F12. Okay, now we say they are equal in magnitude but opposite in direction. Therefore, F12 is equal to negative F21. Okay, they have same value. They have same value. All right, now when you push on the wall, it will push back with the same force. Okay, so if you push the wall, then you have FAB. The wall will push back with the same amount of force called FBA. Now, when it comes to these types of example, usually what I like to do, I seldom use double subscript notation, okay, because it's quite confused. So since my object, the hands is labeled as object A, so what I do is if the hand, okay, if hand push the wall, then I call this FA. Okay, I call it FA. And the wall push back with the same amount of force but opposite the direction, then I call this FB. Okay, usually this is what I call it. Okay, I seldom use double subscript notation because it's different in different books. In your notes, it says force exerted by A on B, but in some other books, okay, I can show you the diagram. In some other books, they use BA. Okay, they use BA. So for example, okay, this one, it uses on by. Okay, on by. So it mentions on first and then followed by. On S by A. So your notes, they use by on. Okay, they use by on in the double subscript notation. So that is what I meant. Okay, some books they use on, okay, on by. So what does it mean? On by? On A by B. Okay, on A by B. But some books they use by on. Okay, so if you have FAB, what does it mean? It means by A on B. So it depends on the books actually. That's why I seldom use double subscript notation. Okay, because every lecturers they have their own opinion. Every books they have their own opinion. So most of the times I encourage my students to use single subscript. Okay, I encourage my students to use single subscript to avoid confusions. Alright, kalau tidak nanti kamu confuse. Sebab buku berlainan, memang cara dia guna pun berlainan. Ada guna on by, ada guna by on. Okay, on by dengan by on, cara dia tulis nampak sama tapi maksud dia berbeza. Okay, so AB on A by B, AB by A on B. So it depends on the books. On your notes, okay, in your notes, they use a second one. And then in university books, the one that I show you, this diagram is from a university books, they use on by. Okay, so if you memorize double subscript notations, then it will be very confusing. Therefore, what I like to do, I like to use single subscript. Okay, I like to use single subscript. So I just use FA or FB. So FA, simple, it means the force coming from A, which is your hand. FB means the force coming from B, from the wall. All right. So in university, it depends on your lecturer, okay, on your professor. See which book they are using. They will give you a textbook. Then you look at the textbook and see which one are you going to use. All right, but in metrics, because of every lecturers, they do their own notes, they have their own notes. Therefore, I don't encourage you to use a double subscript notation because everyone have different interpretation. Okay, now let's see next. Oops. So when the book is placed on the table, the normal force is the reaction force, and at the same time, you have a weight acting in the opposite direction. So provided if it is not moving, we have N equals to W. Okay, N equals to W. So basically that marks the end of chapter 4. All right, chapter 4, you have 5 basic force with 3 Newton's law. So as long as you understand which 5 forces and how to apply these 3 law. So first law, you have summations F equals to 0. Second law, you have summations F equals to MA. Third law, you have F12 equals to negative F21. So this is your 3 Newton's law. All right, and I already explained it to you. Okay, what is the keywords to use in each law? Okay, so that marks the end of today's class. Any questions?
Madam,
Yes.
when we are doing the working for opposite forces, do we need to state out the force like subscript, all that?
You need to state the subscript. You means you need to define it or not?
Yeah, like let's say I write FAB, do I need to write F forces of A is acting on B, like that?
In definition question, yes, you need to write it, but in calculations questions, you don't have to. You just show it in a diagram.
Oh, okay.
Okay. So, any other questions? So if no, I think that's all for today. So you may leave the class and don't be late to your next class. All right, so you may leave the class now. Thank you.
Thank you, madam.
Thank you,
you.
madam.